know we have an atom that has a nucleus, let's say somewhere in the center, and it has these electrons around it. Thinking on our most simple example, which is hydrogen, we have a nucleus and an electron that have to hang together in the atom in some way, and we need to think about, well, how can we describe how atoms behave, and specifically, how do we describe how any single atom stays together where the two are associated, but at the same time they don't immediately collapse into themselves. So what we can do is try using the classical description of the atom and see where this takes us. So if we think about the force that occurs between a positively and a negatively charged particle, what we have is essentially a Coulomb force. So we can describe this as a force of attraction. We can use the Coulomb force law to explain this, where we can describe the force as a function of r. So let's think about what we're saying here. We're describing the force that's holding these two particles together, and it's related to the charge of each of the particles, where E is the absolute value of an electron's charge. So an electron has a charge of negative E, we've written here, and the nucleus has a charge of positive E. And then we have r, which is simply the distance between the two charges. And what we see is that the force is inversely related to the distance between the two charges. And we can simplify this expression as saying negative E squared over 4 pi epsilon naught r squared. Epsilon naught is a constant. It's something you might see in physics as well. Essentially, for our purposes here, you can just think of it as a conversion factor. What we need to do is get rid of the Coulomb tag that we have. That's how we measure our electron charges. So we use this epsilon naught quite often, this permittivity constant of a vacuum, to make that conversion.